just because the 4-year-old has no sense of humor. They laugh at everything, right? My wife sent me that. Okay. Bell work today. We've got a review from yesterday, find the component form, magnitude, and direction of this vector, and then a ACT review question. I'll give you 4 minutes to start this on your, or try this on your own, and then we'll go over it. $300 per day. It's a lot of laughing. Okay. So how do I write the component form of this vector? What do I need to find? It's like the slope, but it's but it's just the components of the slope, the numerator and the denominator. Denominator. I need to find the rise, I need to find the run. That's what you need to do. Am I recording? Yes. The vector and its component form is run, rise, or the change in x, change in y. For our vector, the change in x would be -7 minus -2. And the change in y would be 9 minus 3. So that's really -7 plus 2. So that's -5. 9 minus 3 is 6. So from -2, 3 to -7, 9, we go left 5, up 6. How do I find the magnitude? It rhymes with distance formula. It's the distance formula. So, and since we already have the change in x and the change in y, it's pretty quick. The magnitude of v is the square root of the change in x squared plus the change in y squared. And that is 25 plus 36. Or if you'd rather, 61. Yeah, 61. And again, don't type that into a calculator. Leave it like that. That's how they want it on the old Web of Science. All right, last thing we need is the direction, and that's just the slope, which we already found the rise over run. So that's easy peasy lemon squeezy. It's just 6 over -5. All right. That's everything we covered yesterday, pretty much, minus some notation. Directed line segment discussion, but we feel okay about those 3 things? Well, how about this old ACT question? So table below gives weights, rounded to the nearest pound at birth and at 1 year for 5 boys. A researcher models these weights as a linear function, where the weight at 1 year is dependent on the weight at birth. Among the following models, which is the best? So which of these equations tells me what I should do to x to get the value of y? What do you think? Why did A is right. Why did you say A?
I just plugged in some numbers and decided what my best fit.
That is the easiest. Oh, wait, you did the line of best fit, like in this thing?
You just kind of no, I didn't.
Oh.
You just like estimated.
Yeah, if you kind of just play around with these equations, you'll see that 6 times 3 is about 17. 5 times 3 is about 16. 8 times 3 is exactly 24. 10 times 3 is exactly 30. And 9 times 3 is 27, which is almost 26, right? So that works out pretty nicely. If you spot check the others, you'll see that they're gross, right? Times 4 doesn't work for like any of them. Plus 11 works for this one and this one, but not that one, not that one, and not that one. Not even close. Similarly, plus 16 might work for these ones down here, but not for these ones up here. And then this, I mean, that's just extra. Who's got time for that? 2 times x plus 10. But also if you check, that'd be 12, that'd be 22, that'd be 10, that plus 10 is 20. 16 plus 10 is 26. And all the numbers are closer, but still not where you'd want. The other way you could do this calculator is to actually just find the line of best fit. Do we remember how to do that? No? Well, that's all right. Let me show you. I'll show you. Calculator. Stat. Edit. Enter in our lists into one column, 6, 8, 6, 5, 8, 10, 9. The other list into the other list, 17, 16, 24, 30, 26. And then stat. Go right to the calculate tab. It's option 4. That'll do a linear regression. And if you do that, it'll tell you the best line with a 99 point or 0.99135 correlation coefficient, which is pretty good. Pretty, one would be perfect. So it's just a little short of perfect. Is 2.86 plus 0.86. And if you round those, right, that's about 3. That's about 0. So it's closest to A. Yay. All right, let's talk about vectors. Stop share, reshare, just this screen. Today, what we're going to do, there's also some pretty easy stuff. There's just a lot. Now that we know what a vector is, we're going to start using and combining vectors. We're going to do 2 operators in 6.3, addition and scalar multiplication. If you're going to add 2 vectors together, you will do it exactly how you would think. You're going to add each component together. Let me retype this since it came out kind of small. You just add the change in x's together and you add the change in y's together. Graphically, which you will be asked about on one homework question, what that looks like is if you graph your 2 vectors u and v such that the initial point of v, it begins at the terminal point of u, as you see in this picture. See, they moved v, slid it up, so its initial point ends at the terminal point of u. Then that length across here from the u's initial point to v's terminal point is u plus v. We aren't going to do much with the graphically stuff. It's not going to be on a quiz or test or anything like that. But you might, depending on what physics teacher you get, or I don't know what Miss Mignano likes, or what college physics teacher you might have, they might do more with the graphic component of vectors. So I wanted you to see it. All right, the other operation we're going to do is scalar multiplication, which is multiplying a vector by a constant, which could be any real number. We call that constant a scalar because you're basically scaling it up or down. And to do that, again, it'll work exactly how you would think. If I take a constant k and multiply it by my vector, then I'm going to do k times u1, u2, which is just distributive property. You're going to multiply each component by k. This picture shows then a bunch of examples of what scalar multiplication would do to a graph. So if you had a vector v here and you multiplied it by a half, you'll notice that it gets half as long. If you multiply by 2, it gets twice as long. If you multiply by -1, that switches the direction of the vector. So instead of, going up and to the right, it goes down and to the left. If I multiplied it by -3/2, it would, again, switch directions and get a little bit long. Yay? Does anybody need more time to write these two operators? All right, then let's have you try some problems. So let's say vector v is -2, 5, and vector w is 3, 4. Fine, tell me what 2 times v is, w minus v, and v plus 2w. Again, they will work exactly how you think they would. Nothing surprising. Would it be fun for one of these for the YouTube video if it was like a jump scare? Like it starts out 3 minutes, but then halfway through, it's like a clown shows up and screams. I think people need that in their math class because it's already so like tension free and relaxing. Nobody stresses about, oh, I got to learn all this complicated math stuff. Maybe I'll do that for next year. Okay. Let us, I don't know. Let's do somebody random. Let's 2. All right, Jackson. What did you get for the first one? Yeah, I think you could do it. What do I do with that two? That's right. You just multiply that, yeah, you just multiply the first vector by that. So we're gonna do 2 times -2 and 2 times 5. So that gives us what? -4 and 10? Yay? Okay. All right. Walk us through the second one will be, let's see, okay. Odd for Caitlin, even for Ty, odd for Caitlin. So we're going left today. That's exciting. Caitlin, how do I do this? W minus V.
So you subtract the 3 minus -2,
Yeah,
and then you do the 4 minus.
yeah. And what does that give us? Is that 5 -1?
Yeah.
Yeah, good job. All right, Anna. What about the second one? Look at that. How did you approach this one? Or by second, I mean third one.
So you do b, which is -2 plus 2 times the 3,
Yep, and
and then you got 5 plus 2 times the 4.
yeah. And if you broke this apart, you could also do that. Like if you doubled W first and got 6 and 8, and then add them together, that's fine too, but it's the same thing. And if you do this, what do we get? -2 plus 6, I believe that's 4, and 5 plus 8, 13. Yay? All right, anybody need more time to write? Jackson, you need some time? Oh, you sure? Okay. All right. Okay. You will need to memorize all of these properties. Just kidding. You could just take a picture of it. The only property you really need is this last one. This last one is important. It'll save you some, again, you don't actually, to be honest, you don't really need the last one either. It's just a time saver. It's a shortcut. The rest of these just tell you properties that are interesting to know. And they work, I imagine, how you would think. The first property tells us that vector addition is commutative. U plus V is the same as V plus U. It doesn't matter what order you do them in. The second property tells us that vector addition is associative. U plus V plus W, where you have to do U plus V first, is the same as U plus V plus W when you do V plus W first. It doesn't matter how you group your answers here. You'll get the same answer. The third thing here tells us that 0 is the additive identity. Any vector plus 0 is itself. The fourth option tells us that vector addition is invertible. Invertible. For every vector, there exists another vector, its opposite, such that if you add a vector with its opposite, you get the identity 0. Five, 6, 7, 8, and 9 are properties of scalar multiplication. So you can see that scalar multiplication is associative. It is not necessarily commutative, only really because of style. We don't say a vector times 2, we say 2 times a vector. We've just agreed to that. 6 and 7 both show you the distributive property works. C plus D times U is the same as I can distribute the vector to get C times U and D times U. And C times U plus V is C times U plus C times V. So this actually has a, if you want to be technical, it's left distributive and right distributive, which matters when you have an operation that's not commutative. Do you remember matrices where order mattered, right? And when you distributed, you had to make sure it was still on the left or the right, right? So there's like left distribution and right distribution. Same thing with scalar multiplication. There's left distribution and right distribution. The eighth line tells us that there is a, one is the multiplicative identity, is the scalar multiplicative identity. And 0 is the scalar multiplicative 0. But note that scalar multiplication is not invertible. I cannot take a vector and multiply it by something and get an answer of 1. Because whenever you have a vector and you multiply it something, the result is a vector, not a single number. And then the last one is a shortcut for magnitude. The magnitude of a scalar multiplied by a constant is the same thing as the absolute value of the constant times the magnitude of the original vector. And that'll save you some time when you're doing problems to work it out using that shortcut. But for your trivia nights, that means that vector addition is in a Boolean group and scalar multiplication is not in a Boolean group, which matters for group theory when you take that in grad school math, which I'm sure you all will do. Right, go on to get a bachelor's in math. That'll take 4 years, and then go to grad school in math. And then you'll think back to this time 6 years ago when Mr. Lake told you that vector addition was a Boolean and scalar multiplication wasn't. And you realize, thanks, Mr. Lake. I should send him some money, like $1,000. What? Yeah. I mean, I do that to my teachers all the time. I could send them back $1,000. That has not had any impact on the restraining orders, which I don't understand. I mean, just because it's court ordered doesn't mean it's not a nice gift. All right, everyone happy? If you want, you can take a picture of this slide. To be honest, you won't really use any of this for the homework except the last one. It's just interesting. Gavin, I know you can't see it right now because the camera's facing me, but all of them just like birthday morning interest levels here. Looking at pile of presents, same energy as what's happening right now. Okay. Okay. All right, let me show you this last one. The last one is the one that really matters. So for example, let's say you have a vector 1, 3 and a vector -2, 5. Find the magnitude of each. 2 times u, -5 times u, and 3 times v. So to do this first one, I will do it for you. To find this magnitude, we are going to use the shortcut. I know what you're thinking, Mr. Lake, we haven't done it the long way. The long way would be to actually multiply this by 2 to get 2, 6, and then find the magnitude doing the square root of 2 squared plus 6 squared. The shortcut is I'm going to do the absolute value of 2 times the magnitude of u. To be honest, this shortcut does not save you a lot of time. It saves you like 2 lines of writing. All right, this is the part that messes people up. The absolute value of 2 is +2, not -2. Absolute value is not opposite. Absolute value makes a number positive. So if it already is positive, it will stay positive. And then the absolute value of u is just the distance formula. It's the square root of 1 squared plus 3 squared, which is 1 plus 9 or 10. And again, leave your answer like that. You can't square root 10 without getting a decimal. There are no perfect squares that divide it to 10. So that problem is simplified already. If you didn't do it this way, you would have the square root of 2 squared plus 6 squared, which is the square root of 4 plus 36, or 40. And then you have to worry about reducing the square root of 40 and finding what perfect square goes into 40, which is 4. Square root of 4 is 2. So you'll get the same answer. It'll just take longer. Questions on that? You feel okay about this? All right, this is the last thing we're doing today, I'm pretty sure. No, it's not. Just kidding. Just kidding. There is one more thing. All right, try these two. As a heads up, Ty, you're next up. So you'll do B. And Gavin will have you try C. Okay? Yeah. All right, Ty. What do you think?
So is that an absolute value?
That is an absolute value.
So that should be 5.
Yeah. Times what? Yep,
1 squared plus 3 squared.
that's right. Which is? Yeah, nicely done. Again, if you didn't do the shortcut there, you would have had to done -5, -15, so the square root of -5 squared plus -15 squared, and then find what perfect square goes into that. Which, you don't want to do that. Use the shortcut. Gavin, do you think you could help me out with C? I don't know. I don't think he's up for it. That's okay, Gavin. I'll do it. Absolute value of 3 times the magnitude of V. Absolute value of 3 is 3, not -3. Magnitude of V, I got to use these two numbers here. So I got to do -2 squared plus 5 squared, which would be 3 times the square root of 4 plus 25, or 29. Yay? No? Did you get 21?
Yeah.
Yep. That is a very common, especially if you use a calculator. It'll happen more often, but -2 times -2, positive. Yay? Okay. Next set of problems we're going to do is some application problems. Before we can do those though, let me show you a tool called the unit vector that is pretty useful. All that needs to go in your notes is this. Maybe that little statement too. A unit vector is a vector of length 1. That's why it's called the unit vector. Its magnitude is 1 unit. Its slope or direction can be set to be anything. So what you will usually want to do then is for any vector V, find the unit vector that has the same direction as V. So a vector with length 1 that has the same slope as V. To do that, you could use this formula. You just take vector V and you multiply it by 1 divided by its magnitude. This right here is the most important part, that formula. You take, that's too dark. Let's try a different color. Pink. Yeah. Is that okay? Yeah, it's still kind of dark. Let's try sea glass. Oh yeah, that makes it pop. To 1 divided by the magnitude and multiply it by the vector. That will give you the unit vector. Yay? Does anybody need more time for this line? Okay, let's do an example. For example, let's say this is the last thing we're going to do today. Yeah, this is the last thing. All right. Find a unit vector in the direction of -2, 5, and verify that it has a magnitude of 1. Well, easy peasy lemon squeezy. The unit vector, whoa, no more sea glass. Come on. The unit vector is 1 over the magnitude of V times V. If you look inside the parentheses here, it kind of looks like a birthday cake. Kind of. All right, to do that, we need the magnitude of V. Well, the magnitude of V is just the square root of -2 squared plus 5 squared. Hey, we just did that. That's 4 plus 25, or 29. So we're going to do 1 over the square root of 29. And we're going to multiply that by -2 and by 5. If you do that, you will get -2 over the square root of 29 and 5 over the square root of 29. Okay, I know what you're saying. Mr. Lake, I'm offended that there is a radical in the denominator. How 1980s of them. I will tell you in WebAssign, they're going to accept that answer. On the ACT, they won't. So to fix that, we multiply by the denominator. And so if you get -2 square roots of 29 over 29 and 5 square roots of 29 over 29, that is less offensive to our fragile Western sensibilities. So be ready to do either. All right, so that vector supposedly has the same slope as vector B and supposedly is 1 unit long. But how can we be sure? Well, let's verify that. Let's find the magnitude of U. So we're going to do the square root of -2 over square root of 29 squared plus 5 over the square root of 29 squared. Well, that would be +4 over just 29, right? The square root of 29 squared is 29, plus 25 over just 29. I bet you see where this is going. That's just the square root of 29 over 29, which is 1, and the square root of 1 is 1, don't you know? And so now we can rest assured and sleep soundly tonight, knowing that the magnitude of that unit vector really was 1. Mr. Lake did not lead us astray this time. I mean, it has to have happened. Somebody gave a lecture with a typo, didn't catch it, right? And so everyone in that class left knowing that piece of information, which is actually wrong. But they know, they think it's true because they were told by somebody, right? I mean, I guess that's less likely to happen math because it's easy to verify a lot of this stuff and like, I mean, all the stuff should hopefully make sense to you. If you're like, why does that formula work the way that it does? You can Google it and know for certain, but still. Who's got time for that? You do, because since we weren't able to get to this lecture, the homework is not due tomorrow. It's due Thursday. So tonight you can go home and fact check everything Mr. Lake told you. Right? That's how I got the restraining order. Every night I would go home and fact check my teachers before doing the homework and then tell them what they got wrong. Yeah, I mean, what are you gonna do? Flee the country? Not as easy as it used to be. So I'm just stuck here teaching honors pre-calculus and AP calculus under my alias. All right. Tomorrow, we will finish 6.3, no matter what. Okay, and then Thursday will either be a work day or we'll start on 6.4. I'm not sure yet. Actually, I could probably tell you pretty quick. Let's look. How long do they say for 6.4? They say 2 days. I don't think I want to start 6.4. Tomorrow will probably be a work day, and then Friday will be a quiz. Because I won't be here Friday. Figured that would be a good use for our time. Or maybe I could just let the quiz go tomorrow and Friday, like give you both days to work on it. That's probably smart. Or by tomorrow, I mean Thursday and Friday. That's probably smart. Yeah, Mr. Lake solving problems right now. So tomorrow we finish 6.3. Thursday and Friday will be a quiz. And Friday I won't be here. You'll have a sub. Yeah.